Hey everyone, Dr. Calkins again. We're going to wrap up Chapter 3 talking about electron configuration in the context of ions. And an easy way to see ions is noble gas configurations, which is just a shorthand version of electron configuration using noble gases. And then show you how those work together to make a compound in the end. So let's start by looking at electron configuration. Last time we saw carbon, so let's do that one more time. So in our carbon, we have the first row of the periodic table, which was a 1s2. You go to 2s2 in the second row, and then you go to 2p2. That's 6 boxes in the periodic table. And really, if you want to cheat on this, you can just go 2 boxes, periodic table, start over, go 2 boxes, start over, go 2 boxes. So if we were to look at the periodic table and cheat off just the superscripts, that's exactly what we're after. We're saying go 2 boxes, go 2 boxes, go 2 boxes, and you're going to find carbon. So that's electron configuration. This understanding that if we have a carbon atom, it's going to have 6 electrons in those positions of the periodic table. But if we want carbon to be happy, we want it to be noble gas-like. So the noble gas-like, or at least the noble gas closest to carbon, is neon. So neon has a configuration of 1s2, 2s2, 2p6. Turns out there's something magical about having those 8 electrons in that outer level. So if we understand that that's really what neon has, is this magic number of 8 in the outside, it's got 10 total. What would it take for carbon to do that? Well, in order for carbon to do that and become a 1s2, 2s2, 2p6, this number needs 4 more. What do you think those 4 represent? Those 4 represent electrons that needed to be gained in order to turn 2 into 6. So in our case, carbon loves a -4. If carbon loves a -4, this is what we would call carbide in a later chapter. So as we look at neon and look at carbon, we just realize all elements want to be like noble gases. It's just our job to figure out which direction they need to go. So let's try one more example. If we have sodium. Sodium loves a +1. Let's see if we can figure out why. If sodium, just the element sodium, is 1s2, 2s2, 2p6, that's neon. That's the first 10, but sodium is number 11. So we go to the third row, the first box, that's the S1. But if sodium loves +1, why is that the case? Well, notice we have something extra. We just need to lose this electron to become sodium +1, and we become 1s2, 2s2, 2p6, just like neon. So we can use electron configuration to figure out what ions want to become, because they're either going to move left or right in the periodic table to match that noble gas-like configuration. So as we represent this in a shorthand version, another way to write sodium would be to take its noble gas and just call it neon in brackets. So if we took sodium, no charge, it would be neon 3s1. Just like if we were to take carbon up here, so let's bring carbon down. If we were to bring carbon down and say, all right, carbon is 1s2, 2s2, 2p2. Its noble gas is helium, the first 2 electrons, and 2s2, 2p2. One thing I like about noble gas configurations is they're telling us what's on the outside. They're saying that this is the core, just like this is the core, and this is left over. So if this is left over, that means it has 1 valence electron. But really they're just saying that's in family Roman numeral 1. That's in group 1. That's what it means to be an alkali metal. Carbon, however, it has a different position in the periodic table for a reason. It has a helium core, but it has now 4 electrons in the valence. And what that tells us is if carbon has 4 electrons in the valence, that would just be Roman numeral 4. Or, in this case, just group 4. And if that's in numerical order, it would be 14. So whether it's Roman numeral or just numerical number, Roman numerals tell us how many electrons, so that's a faster way to get to what electron configuration tells you. So just know that if you're looking for valence electrons, look for Roman numerals. That's a faster way than just looking at electron configuration and going through all that amount of effort. So let's show you an example of how things can work together. So oftentimes, students want to know what happens when magnesium and oxygen go on a date. So X and Y. The answer is OMG, right? In any case, let's prove it. So if we're going to prove this, we need to know why they want to get together in that kind of pattern. So let's do their configurations. Magnesium is 1s2, 2s2, 2p6. And again, that's neon, but as we go to magnesium, we need to go 2 further. That's 3s2. Let's do oxygen. Oxygen is 1s2. First 2 boxes, go to the next row. 2s2, notice, identical. Gets tedious after a while. And then to count over to oxygen, you're going to count 4 boxes, so that's a 2p4. Oxygen is number 8, and we add up to 8. Just like over here, we added up to 12. So that's what they are as elements. What if they met each other for the first time, much like we did when we had the Bunsen burner? We lit magnesium on fire and made magnesium oxide. Let's see what happened behind the scenes. So let's first take magnesium and do the noble gas configuration. So let's take the noble gases. Here's helium, here's neon, so let's write, this is just neon, 3s2, that's its shorthand conversion, so it's noble gas core configuration. Do the same thing over here. We're not quite to neon, so we're going to have to chop here. That would be a helium, 2s2, 2p4 for oxygen. And if these two were to meet in the air with a little bit of heat, guess what happens? Magnesium says, I really want to be like neon. If I really want to be like neon, I need to get rid of these 2 electrons. Where do you think those 2 electrons want to go? Well, over here, oxygen says, well, I have 4 in my p orbital, but I also have 2, so that's 6 total. That's in Roman numeral 6 family. I could lose all 6 and be like helium. Or if you remember, neon was just a 6 here. I could take these electrons and I could be noble gas like 2. If that happens, magnesium loses 2, so it becomes a +2. And more importantly, it feels as if it is just like neon. It can never be neon because it can never be a noble gas based on its number of protons. But now it can feel like neon. Over here with oxygen, because this 4 became a 6, oxygen became a -2. And that's because it became 4 into 6, so that really would just mean it too became just like neon. Add the 2 electrons here, 2 more, that would have been its 8. Added 2, that's 10, just like what now magnesium is. And it turns out when you bring these together in the formula, it's 1 magnesium to 1 oxygen, actually MgO, not as the even now lamer joke, OMG went. So this is how we understand ions. We can use electron configuration to predict the ions that are made. Just know that sometimes there's a mismatch, but this is the theory behind how all compounds are formed. Let's show you a shortcut. If we look and create a generic periodic table, I'm not going to worry too much about the electrons in the D. We drew this on our supplemental 5. Remember, group 1 is a +1 and a +2. We saw magnesium, and that position is +2. Now we know why. Dark line definitely matters. That's where things change. Again, no charge here for the noble gases. We're trying to get there. We have a -1, a -2. That's what oxygen wanted, and oxygen's location's right there. -3, -4. I'm not going to worry about boron. We don't really deal with it in Intro Chem. +3, +4, and again, these are things we don't worry about either. But that descending trend is all because of what we talked about up here. So if we know that this is the end game, why not just jump straight to this, knowing that electron configuration helped us get us there, and do examples. So if we were to take, say, lithium and a fluorine, X and Y, just the numbers that we need to find out. If you find lithium over here, keep in mind hydrogen's here too. Lithium sits here, fluorine sits here. That's really just a +1, -1. They cancel and make lithium fluoride. Let's try a different one. If we were to take, say, calcium and nitrogen. Well, calcium's really just sitting over here, kind of right in front of where that 2 was, next to those transition metals. But then nitrogen sits over here. So if we have really just a +2 on the calcium and a -3 on the nitrogen, that charge isn't the same. But what do 2 and 3 have in common? They have 6 in common. So to get 6, we need to multiply this by 2 and multiply this by 3. So if that's +6 and that's -6, that'll cancel, but that's a lot of math, and even though I took calculus 1 through 3, I don't really favor math either. And wouldn't it be nice if there's a shortcut? Well, the shortcut is really just, if that's the math, isn't that really just taking this number, moving it down, and taking this number and moving it down? We get calcium 3 times, nitrogen twice. That's actually called the crossover rule. You'll do that when the charges are different. You don't need to do it when the charges are the same. If you would, you just reduce. Let's try a couple more examples. We can cheat with some examples like hydrogen and oxygen. Even though this is a covalent compound, it does fit these rules because hydrogen can be lost in molecules like this, and we'll see which one we're about to make. But again, hydrogen kind of sits up here, so we can use that as a +1. Oxygen sits over here, we can use that as a -2. And because the charges are different, don't worry about the math, just let the numbers do the work for you by crossing them down, turning them in from superscripts into subscripts, and now notice we just get H2O water. So that's why water has the formula that it has. Last example, if we have carbon and oxygen, even those can pretend the rules even though they're in a thing called a covalent compound typically. But again, because they have charges that are represented, they can actually work in this situation. So again, oxygen is a -2 being in that family. Carbon is in a -4, which is weird, but carbon does have a unique position. It could gain 4 electrons to be like a noble gas, or because the magic number is 8, gaining 4 is possible, but also losing 4 is also possible. So carbon really likes both charges. And in order for this one to work, we would definitely want to think of it in a positive context. But even then, you can cross charges, get to a C twice and O 4 times. But the problem is, when you have numbers that you cross, you still have to worry about, can they reduce? And carbon dioxide would be the answer now, once we reduce by the multiple of 2. So ions can be quickly figured out if we have a handle on the increasing pattern of charge for metals and the decreasing pattern of charge for nonmetals. If they're the same, squish them together. If they're different, cross them. And then when you cross them, just watch out, sometimes you can reduce them. And that kind of wraps up our week 3, chapter 4.